In the meantime, I'll just mention that doesn't talk. The center's name is indeed quantum information and quantum control. And often when I speak with universities, people, they are a little bit unhappy about the control because they hear a lot about quantum information, but they keep asking, what's the control about? So it's great to hear so many quantum control talks and make the point that that's the key for getting the quantum information. So Farzad, Ghafari, sorry. Yeah, we'll talk now, and I guess you get the prize for traveling the furthest away.
Yep.
Yeah, thank you very much then, and please.
Yeah, thank you very much. Can we make that? Yeah. Great. Okay, so thank you very much, and thank you for staying for the almost last session of the conference, and the organizer for giving me the opportunity to present some of our recent works at Griffith University. So I come from Griffith University in Brisbane, Australia, from Quantum Optics and Information Lab. And this is a collaboration between Griffith University and University of Queensland as part of the Center for Quantum Computation and Communication Technology. So if you want to know a bit about Brisbane, we are located here. This is the city. If you drive 45 minutes, you get here, and you might be able to see some kangaroos around. But if you are not interested in touristic stuff, please come for science. All right, so I actually have a very simple task here to present my work, because the task that I'm pursuing to do is share an entangled state between two parties. So entanglement is such a valuable resource in quantum information and quantum communication, and sharing entanglement is very important, therefore. But the problem is that if it was easy, then we could have had something like this up to now. Like, we probably have built a quantum network up to now. But unfortunately, going back to the simple task, we are still struggling to finish this task properly. And the reason for that is mostly loss. So when you are dealing with loss, basically you lose entanglement. And when you lose entanglement, you lose the resource for quantum communication. And not only that you're losing your information, basically your communication is lost, you also open the door for eavesdropper and attacks. Basically, if you lose one photon that is going from Alice to Bob, the eavesdropper can get that, and you don't know if the photon is genuinely lost or the eavesdropper actually has got it and abused the channel. So that is why overcoming loss is such an important task in quantum communication. So now, in classical communication, what we do in like everyday fiber networks, we have these amplifiers. You send a signal in. If you can move this thing, yep. You have an input signal, you have a you have an optical amplifier, and then you basically have an output signal which is amplified. But unfortunately, this is not doable in quantum physics. It is forbidden by laws of quantum physics, what we know as no cloning theorem, which says that you cannot basically clone an unknown quantum state perfectly. And this perfectly means that with high fidelity and deterministically. So there is two things, fidelity and determinism. And you have to go for one of them. So because the integrity of information is such an important thing in communication, then we have to take the high fidelity and basically leave the determinism. So we go with probabilistic high fidelity schemes. So that is what we do in quantum amplification. All right, so most of what we know today about quantum networks, like all of this news, like about like 1,000 kilometers or like 500 kilometers, they all actually have a caveat. They all rely on these classical trusted repeaters, where the amplification happens is actually classical. What happens here, so you have your quantum information comes to these trusted nodes, you measure them, convert them to classical information, and then re-encode, amplify them, and then re-encode them into classical channel. So the problem with that is, first of all, if you convert your information from quantum to classical, you would lose a lot of quantum advantage that you know about channel capacity or like dense coding or those kind of stuff. That's one problem. But the bigger problem here, so the bigger problem here is that if this trusted node is breached, you basically lose all of the quantum information and communication advantage. So you have to keep this node trusted. And what is the dream? The dream is that to actually realize something like this, to realize a quantum repeater which doesn't need converting information from quantum information to classical information. So a very simple scheme for a quantum repeater is something like this. So we have two parties, Alice and Bob, who wants to share an entangled state. So you have two sources of single photons, let's say, which each of them have a pair of entangled particles. One of these particles goes to like the distance party, Alice and Bob, from each source. One goes here and one goes here. And then there is a quantum memory here, which holds these particles and then does an interference or a measurement, which is basically a Bell state measurement, and there is this classical communications, and there are some local operations based on this like measurement results. Okay, so this is basically the holy grail of quantum communication. If we can build this, then we are almost there. But still here, we have to combat errors that come from noise and loss. And there are different approaches to go about this. There are error detection and error correction codes for this, like basically to combat error here. But they only can work in low noise regime. If your loss goes beyond like some threshold, you can't fix it with error correction. So the other approach is that basically using some sort of entanglement purification or entanglement distillation protocols. And that is what I'm talking about today. I basically talked too much, but I came back to my first slide again to say why I care about this thing. So again, I have two parties. One of the parties is sending an entangled state, or two parties want to share an entangled state, and we are dealing with this loss here, which is basically eta, I call it. The transmittivity of the loss is eta. And then, so we can do nothing. Basically, if you do nothing, your entanglement gets a little bit fuzzy, and then you probably can't do any communication. But instead of doing nothing, I mean, before going forward, I just wanted to basically not do all of my talks in cartoons and give a bit of quantum optics here. So in linear quantum optics language, basically this translates to something like this. So Alice has a state in two modes, A and B. Then you have this beam splitter here, basically, which makes a single rail entanglement. And then you have this loss, which is actually modeled by another beam splitter. As I said, the transmittivity is eta, and obviously this goes to dump. And then you have the bob, which receives this state. But the final form of the state is something like that. And so this tau here basically and eta here determines how much of the state Alice and Bob get and what is the entanglement here. So this is, as I said, like more like a quantum optics language. Okay, so but instead of doing nothing, we can actually do something called noiseless linear amplification, or the distillation that I talked about it. So in this protocol, we still have Alice trying to share the entangled party, but this time Bob also has an ancilla entangled state, right? So what happens is basically we have this interference between Bob's ancilla state and Alice's state going through loss, and if and only if there is one click in this heralding station, then there is an entanglement shared between Alice and Bob. So this is actually again a quantum optics language. So this is Alice, this is loss, this is Bob preparing the ancilla here, and then you have the heralding station or relay. And if there is one photon in either of mode C or B, then you have an entanglement shared between mode A and D, which is the stations that Alice and Bob hold. So this work has been realized already almost 15 years ago and has been published in Nature Photonics, right? It's all good. And why I care about this work again. So now in 2021, I guess, people, I mean, not people, Tim Rolfe, basically asked this question that what if we move this relay station somewhere in between, right? So in the previous scenario, basically Alice sends his state, her state, goes through all the loss, and Bob is holding the relay station. But now the question is that, what if we bring this relay station somewhere in between Alice and Bob, where her state goes through a square root of loss, Bob's state goes square root of loss, and what happens then? And again, if we have one photon at this heralding station, then there is an entanglement sharing between Alice and Bob, but the difference this time is that the probability of success of the protocol is actually higher. Remember, I talked about fidelity and probability of success, and I told these are two important parameters for doing this this kind of entanglement sharing protocol. And by just moving the relay between two parties, you can improve on the probability of success. So as you can see here, so the probability of success, and this is basically the translation of loss to distance in fiber, okay? So you see for both cases, like when you have this like x equal to 10 and x equal to 50, for both cases when the relay station is in the middle, you can improve the probability of success. Just a quick word on x. X is basically the purity of the state. And the purity of the state is, if I get a click here, which is the herald, and says, all right, the purification is done, what is the chance also there is still a state for Alice and Bob? If you lose that state, the purity of the state basically drops. If you get the state, then everything is fine. All right, so I talked about purity of the probability of success, but you might ask, why do I care about probability of success so much? So imagine in this scenario, you have a lot of these imperfect state or not distilled state, and you want to do a distillation protocol until you have a distilled state with like basically purity 1. So you start with 2 of them. You distill them with probability P, and then another 2, and another 2, and another, and use the distilled state for resource for the second round and third round, and so on. But if the probability of distillation here is P, you can see that basically this probability grows exponentially, and any improvement on this probability P actually saves you a lot of resource. And that is why improving the probability of success for these distillation protocols is quite important. So now, after all, I'm an experimentalist, and I try to do this protocol in the lab. So this is the experimental scheme, which I use single photon sources. If you have been through the talks during this week, you might have heard about SPDC, or a spontaneous parametric downconverger. So we basically have these two photons in telecom wavelengths, and then I just call one of these arms Alice, one of them Bob. Then you have like these interferometers where we can implement a variable loss. And as I said, you have like basically Alice goes through the loss, Bob goes through the loss. This is the central interference. This is the relay or heralding station, and this is the output state, which is shared between two parties. All right. So the experiment, basically, when we started the experiment, we thought, okay, this is a relatively simple experiment, but like anything else like everything else in the lab, it wasn't as simple as we thought. So to be able to realize such an experiment, you really need two very important factors. So first, you need a very high efficiency source. And for people who are working in this field, like they know like having a source with efficiency above 80% is quite impressive. And the reason for that is that if there is a heralding photon here, basically that herald the purification is done, then we really want to have another state here. And if that's not happening, you are basically reducing the purity of the state. So that is why we need high efficiency source, and then also we need to have a very dark count in your single photon detectors. So the reason for that is because we are basically working in a very low loss regime. In a low loss regime, the signal that you're getting in the actual experiment is very comparable with the signal that your dark count is giving. And if your dark count is comparable to your real signal, basically your signal to noise ratio is bad, and then you have a problem. So that is why keeping the dark count also very low is important. So we did the experiment, and these are some of the basically results. So in the left-hand side, I'm showing probability of success versus the transmittivity of the channel. This is 1 minus loss, basically. So in the left-hand side scenario, Alice is sending a maximally entangled state to Bob, and Bob is tuning his ancilla entangled state to maximally entangled state. There is no control on Bob. Basically, what we call in this NLA protocol as gain, Bob is only sending a maximally entangled state. So as you can see here, even here, we have this like nice improvement on the probability of success when we move the relay station in the middle. So that's good. But as you can see here, for very, very low, very high loss or low transmittivity area, we don't have as good as a result. And as I said, here is the place that dark counts play a role. And here also is the place actually the NLA doesn't work very well. So in a low loss regime, these distillation protocols don't work very well. In the right-hand side, we also have another result, but in this scenario, Alice again sends a maximally entangled state, but this time Bob has a control on their ancilla, and they can basically change it a bit to make sure they get the maximally entangled state with highest fidelity to be shared between them. And here here we see a better improvement in the probability of success, but again, you can see the same trend in the very high loss and low loss regime. So I didn't talk about fidelity much. I mentioned about this like two factors, fidelity and probability of success, and I said fidelity is important and probability of success. But most of my talk was about probability of success, but to make sure we actually are sharing a very good state between these two parties, I only actually chose or filtered the data to have the high fidelity result, and the low fidelity result, which shows a better improvement in the probability of success, is not included. So by that, I close my talk to say, so we have shown that by moving the relay, you can improve the probability of success. And but there is still a lot of work to be done. The experiment was very challenging. We still don't completely see the result here because this is like, as I said, this is like a theoretical physicist dream, but in the lab seems to be way more challenging to realize this result. But we need to understand why our results are not exactly meeting the theory, and there are some theory study is going on to understand the experimental result better. So with that, I hope you enjoyed the talk, and next time you have the problem, please move the relay further, not the closer. Thank you.
Thank you very much.